Mysterious metrology of the ancient world. You are listening to Brothers of the Serpent podcast.
And welcome back, ladies and gentlemen, boys and girls, angels and demons and monsters and serpents. This is Brothers of the Serpent podcast, coming to you not live from the 10 by 10 by 10 tangent cube of science, nestled amongst the dusty bones of an ancient seabed high atop the Everest Plateau, and I'm not actually here. It's just Kyle this week.
This is a fantastic beer.
So yes, we're actually recording this early because I am going to be I'm flying out tomorrow, which is Thursday of the same week that we just published the last episode, because I'm going to be staff on one of Randall's tours over there in Middle Cumberland.
Heck yes.
Yeah. So, nope, no space for the news. Nope, no agricultural news, no rock and roll news, no crypto update, because it's not next week yet. So... We got a cool story that Kyle found that we're going to go through, and then I have some, peripheral things raining out of the sky stuff that we can talk about.
Well, why don't you do your news stories first, and then we'll jump into this.
Okay.
Into the main topic.
Yeah.
Do we
Hi, by the way, I'm here.
Oh, and the Watcher's here.
Oh, yeah, the Watcher's here. That's right. Yeah. From deep beneath his secret space station.
Scared the crap out of me. You just showed up out of nowhere. Not used to it.
So first, I was looking up, just stuff raining from the sky. Here's one. Texas witnesses a rare weather phenomenon as fish rain from the sky. This is from IndianExpress.com. This phenomenon, known as animal rain, is said to be caused by tornadic waterspouts.
Tornadic.
It's raining cats and dogs, the saying goes, but in Texarkana, a city in Texas, it rained fish on Thursday.
Oh, I was believing it until it was Texarkana.
And it doesn't say what day on Thursday, but this article, I'm pretty sure
those people can't even figure out where they're from.
I'm pretty sure this was right at the beginning of the year, 2022. So it says, reporting about the bizarre meteorological phenomenon, the official Facebook page of the city of Texarkana, Texas, said 2021 is pulling out all the tricks, including raining fish in Texarkana today. So based on when this article was published, which is January 4th of 2022, I think this must have happened at the end of 2021. Elaborating, they explain on the Facebook page, animal rain is a phenomenon that occurs when small water animals like frogs, crabs, and small fish are swept up in waterspouts or drafts that occur on the surface of the earth, and then they are rained down at the same time as the rain. While this is uncommon, it does happen, as evidenced in places in Texarkana today. This Facebook post has been widely shared with thousands of shares and hundreds of comments, and no one cares about that. But there's a couple of pictures on here of the fish. It's not raining tadpoles or guppies, this post says. It's called animal rain, and of course, it's happening in Texas. And the fish is like, they've got their foot next to it, which is not helpful because you can't tell how big the foot is.
About 6 inches, maybe.
Yeah. Many Texarkana residents took to social media to document the dead fish lying on roads and in their backyards. Some people were amused. One person commented, "There are probably a lot of happy stray cats," on one post, while another said, "People thought I was crazy 20 years ago when I told them it rained frogs at my hog farm. I stood there dumbfounded looking at my concrete walkways being covered as they were falling.
Wow.
I was wondering if the world was coming to an end."
So they found a guy who actually witnessed another fall.
Yeah.
That's cool.
However, some people are worried about the health and hygiene issues that dead aquatic animals might cause if cleanup operations are not done on time. Animal rain has previously been reported in places like California and northwestern Serbia. That's the end of that article. So that's great. I mean, that's very recent.
You just need an umbrella made of razor blades, and you have instant sushi.
That's true.
Yeah.
Or a really good samurai just standing out there in the rain with his sword, right? All right, so I looked up red rains also, and this excellent Wikipedia article came up called Red Rain in Kerala. It says the Kerala red rain phenomenon was a blood rain event that occurred in Wayanad district region of Malabar on Monday, 15th July of 1957. The color was red and it subsequently turned yellow. So this sounds familiar, right? And also 25th of July to 23rd of September 2001, when heavy downpours of red-colored rain fell sporadically on the southern Indian state of Kerala. Again, staining colors or clothes pink, yellow, and green, and black rain was also reported. Colored rain was also reported in Kerala in 1896 and several times since, most recently in June of 2012. See, I knew there was a 2012 one. Because this was, people were like, it's the end of the world, right? It's raining blood. And from 15th of November 2012 to 27th of December.
And in that case, they had tinfoil umbrellas.
In 2012 in eastern and north central provinces of Sri Lanka. Following a light microscopy examination, so the god of microscopic analysis was consulted in 2001. It was initially thought that the rains were colored by fallout from a hypothetical meteor burst. But a study commissioned by the government of India concluded that the rains had been colored by airborne spores from a locally prolific terrestrial green algae.
The algae again.
The colored rain of Kerala began falling on 25th of July 2001 in the districts of Kottayam and Idukki in the southern part of the state. Yellow and green and black rain was reported. Many more occurrences of the red rain were reported over the following 10 days and with diminishing frequency until late September. According to locals, the first colored rain was preceded by a loud thunderclap and a flash of light, and then followed by groves of trees shedding shriveled gray burnt leaves. Shriveled leaves and the disappearance of and sudden formation of wells were also reported around the same time in the area. This rain typically fell over small areas no more than a few square kilometers in size and was sometimes so localized that normal rain could be falling just a few meters away from the red rain. Red rains typically lasted less than 20 minutes. Each milliliter of rainwater contained about 9 million red particles. Extrapolating these figures to the total amount of red rain estimated to have fallen, it was estimated that 50,000 kilos or 110,000 pounds of red particles fell on Kerala.
So that's the marksmanship he talked about.
Yeah. The brownish red solid separated from the red rain consisted of about 90% round red particles, and the balance consisted of debris. The particles in suspension in the rainwater were responsible for the color, which at times was strongly colored red. A small percentage of the particles were white or had light yellow, bluish gray, and green tints. They were typically 4 to 10, what is that?
Nanometers
across. Micrometers, spherical or oval. Electron microscope images showed the particles as having a depressed center. At still higher magnification, some particles showed internal structures.
I guess it would be microns or something.
Could be microns. Yeah.
It's
Yeah.
I'm pretty sure it's micron or micrometers.
Initially, the Center for Earth Science Studies stated that the likely cause of the red rain was an exploding meteor, which had dispersed about 1,000 kilograms or 1 ton of material. A few days later, following a basic light microscope. What did you say that was? Microscopy. That's it. Microscopy evaluation. They retracted this as they noticed the particles resembled spores. And because debris from a meteor would not have continued to fall from the atmosphere into the same area while unaffected by wind. A sample was therefore handed over to the Tropical Botanical Garden and Research Institute for Microbiological Studies, where the spores were allowed to grow in a medium suitable for growth of algae and fungi. The inoculated.
That's cool.
Yeah, inoculated petri dishes and conical flasks were incubated for 3 to 7 days, and the cultures were observed under a microscope. In November of 2001, commissioned by the government of India's Department of Science and Technology, the Center for Earth Science Studies and the Tropical Botanical Garden and Research Institute issued a joint report, which concluded the color was found to be due to the presence of a large amount of spores of a lichen-forming algae belonging to the genus Trentifolia.
See, this is what I've been saying, man.
What?
Plants have been conspiring to have sex with all of us for a long time.
That's right. Field verification showed that the region had plenty of such lichen, and samples were taken from the area when cultured in an algal growth medium. They also show the presence of the same species. So there you go. And there's a whole bunch more on this wiki page.
I wonder how high up those like clouds of that. I mean, they had to be so dense too. To
I don't
color
know.
it red.
Here under alternative hypotheses, they have this. This is cool. History record.
But like to be a good what is it called? What is
intermediatist?
Intermediatist. It's like they found. I mean, how many other particles of things did they exclude?
Right. And he says there were
From the raindrops.
Yes, and it says that black rain, yellow rain, and other colors were also reported. They studied those as well. And was it the same material? Is it all the spores of this same stuff causing all these different colors?
His point is that
they would exclude
stuff. They find a few spores of something within there that are that color or something, and they're like, well, this is
what's causing it.
Yeah.
And they ignore all the other stuff that's in there. Yeah, this said the rest of it was debris. Unnamed debris. History records many instances of unusual objects falling with the rain. In 2000, in an example of raining animals, a small waterspout in the North Sea sucked up a school of fish a mile offshore and deposited them shortly afterwards in the United Kingdom. Colored rain is by no means rare and can often be explained by the airborne transport of rain dust from desert or other dry regions, which is washed down by rain. Red rains have been frequently described in southern Europe, with increasing reports in recent years. One such case occurred in England in 1903 when dust was carried from the Sahara and fell with rain in February of that year. At first, the red rain in Kerala was attributed to the same effect, with dust from the deserts of Arabia initially the suspect. LiDAR observations had detected a cloud of dust in the atmosphere near Kerala in the days preceding the outbreak of the red rain. However, laboratory tests from all involved teams ruled out the particles were desert sand. A senior scientific assistant in the Indian Meteorological Department proposed dust and acidic material from an eruption of Mayon volcano in the Philippines as an explanation for the colored rain and the burnt leaves. The volcano was erupting in June and July of 2001, and this scientific assistant calculated that the eastern or equatorial jet stream could have transported volcanic material to Kerala in 25 to 36 hours. This hypothesis was also ruled out as the particles were neither acidic nor of volcanic origin. A study has been published showing a correlation between historic reports of colored rains and of meteors. The author of the paper, Patrick McCafferty, stated that 60 of these colored rain events, or 36% of them, were linked to meteoritic or cometary activity, though not always strongly. Sometimes the fall of red rain seems to have occurred after an airburst, as from a meteor exploding in the air. Other times, the odd rainfall is merely recorded in the same year as the appearance of a comet. Panspermia hypothesis. In 2003, Godfrey Lewis and Santosh Kumar, physicists at the Mahatma Gandhi University in Kerala, posted an article entitled "Cometary Panspermia Explains the Red Rain of Kerala." While the CESS report said that there was no apparent relationship between the loud sound, possibly a sonic boom, and a flash of light, which preceded the red rain, to Lewis and Kumar, it was a key piece of evidence. They proposed that a meteor from a comet containing the red particles caused the sound and flash, and when it disintegrated over Kerala, it released the red particles, which slowly fell to the ground. However, they omitted an explanation on how debris from a meteor continued to fall in the same area over a period of 2 months while unaffected by winds.
Wow. But who has anyone tried to explain that?
Right. How do you explain that with the spores?
Explain it? Yeah.
I love how they point that out when it comes to the meteor dust, but not with the other stuff that is said to explain it. Anyway, there's a bunch more here on alternative hypothesis, cosmic ancestry. They reference Chandra Wickramasinghe in here. And some criticisms of these ideas, of course.
Our good buddy Shand.
Yeah. So, good article. Red Rain in Kerala on Wikipedia.
Cool.
And I have one other one. This one's not raining, but it is somewhat Fortean, and it is recent. This is from SmithsonianMagazine.com. Large parachuting spiders could soon invade the East Coast. Study finds. The authors say the arachnids are harmless to people and pets and may even eat pests like stink bugs. This was posted on the 8th of March, so a couple of days ago. Yeah. 2022. So this was posted yesterday. Last year in Georgia, the non-native Joro spider population exploded. Golden webs draped porches, power lines, and mailboxes across at least 25 counties in the state. I have several hundred, says Michelle Hatcher, and they actually... Or wait, no, this is an entomologist. I have several hundred, and they actually make the place look spooky with all the messy webs, like a scene out of Arachnophobia, entomologist Will Hudson of the University of Georgia told the Herald last fall. The spiders are large and eye-catching, about the size of a human adult's palm, with bright yellow, blue, and red colorations.
That's a big spider.
And they can fly. These arachnids form parachutes out of their webs, and they can travel 50 to 100 miles with wind, per the University of Georgia Extension report. With the Joros quickly conquering the state, the University of Georgia researchers Andrew Davis and Benjamin Frick wondered how far north the spiders would spread. Their new study, published in Physiological Entomology, found that Joro spiders can survive in colder temperatures, making it likely that the species will take over much of the East Coast.
Oh my gosh.
There's one. Look at that. Beautiful, bright colors.
The size of a adult human palm.
Yeah, I guess it's like we have garden spiders that are like that, right? With their legs.
But they can fly.
Yes, these can fly.
We need to get some spider-eating snakes. Let the spider-eating snakes loose.
Researchers compared the Joro spider to the golden silk spider, a species in the same genus that has not expanded beyond the southeast per the study. They also looked at data collected on iNaturalist, which is a citizen science website and app that collects data on the location, species, and times of a wildlife sighting. Then the researchers measured traits like metabolic rates, heart rate, and survival during below freezing temperatures to help predict female spiders' tolerance to cold. Compared to the golden silk spider, Joros have a 77% higher heart rate when exposed to lower temperatures, have doubled the rate of metabolism, and are more likely to survive a brief freeze. The spiders also have a shorter season, meaning they can complete their life cycle within a narrower period. So it looks like the Joros could probably survive throughout most of the eastern seaboard, which is pretty sobering, Davis said in a statement. Some scientists say East Coasters have nothing to worry about. The spiders haven't shown any signs of disturbing local ecosystems. They don't hurt humans, and they even eat pests like stink bugs. This is wonderful. This is exciting. Spiders are our friends, says Nancy Hinkle, an entomologist at the University of Georgia. They are out there catching all the pests we don't want around our home, but not all scientists are enthusiastic. You really don't know if this is displacing native stuff or not, Dave Coyle says. He's a professor of forest health and invasive species for Clemson University. So personally, I'm not prepared to say that it's not harmful, but I can say that it's not harmful to people or pets. Joro spiders are native to Japan. They arrived in the United States around 2013, likely riding on shipping containers or flying across the ocean, which they don't say in the article. There's really no reason to go around actively squishing them, Frick says in the statement. Humans are at the root of their invasion, so do not blame the spider. There you go.
Blame the humans. But yeah, I don't like killing spiders.
I don't either. They are our friends. Like I was telling the watcher earlier, the only spiders that aren't our friends are the ones that eat birds, because birds are our friends. I judge friends to be anything that eats bugs. Spiders eat bugs, friends. Birds eat bugs, friends. Spiders that eat birds that eat bugs, not friends.
Dude, all I'm saying is palm-sized flying spiders that can go 100 miles is a sign of the end of days, bro.
Especially if they're raining down from space. Because then they're actually...
We need to hybridize a snake with a chicken so that the snake can fly, and then there would be a massive war in the skies.
Yes.
Bro, how do you take a flightless bird and make a flying
spider
snake?
eating snickens?
Because it could be an out what do they call it? The traits that are like larger than the thing could be. I can't remember what it's called.
Chicken wings. Chicken wings would be able to support flight on a smaller.
Well, no,
snake.
it's when you hybridize things. Sometimes there are
traits that are outside of the parameters of either of the parent species.
There's a name for it.
Yes.
Who knows it? Email us now. Thank you, Ann.
let me go find.
I can't remember what it is. But anyway, yeah. You cross a snake, you make a snicken, and it'll fly, and there will be a massive sky battle between these spiders and snickens.
God, that'll be amazing.
It'll be freaking awesome to watch.
Yes. And that will let us know that the end of days are nigh.
That's right.
Flying snakes fighting giant spiders.
10,000 years from now, you'll find rock paintings of giant chicken snakes.
Snickens.
Going at it with the golden web spiders.
That's right.
Oh, the golden web spiders.
And
jeez.
And the archaeologists of the future will say, oh my God, they were all on shrooms.
Snickens fighting flighters.
Sliders.
All right. let's get serious here. Kyle's got some serious stuff to look at.
No, this is we don't have to be serious, but this is a really cool article. It's on ancient-origins.net.
Yes.
The title is A Rediscovered Unit of Length and Implications for the Neolithic. And there's a lot in here. I read this article approximately 10 days ago. As the watcher pointed out, that this article is 10 days old, but it was recently updated. So there's a lot to talk about here. We could go through the whole thing. But I feel like there are portions of it that may require us to figure out what's going on.
Okay.
Live, but not live. And also discuss. So, yeah. So it begins. Following work, which began in the 1970s and spanned nearly 40 years, Peter Harris and Norman Stockdale identified a new unit of length, new is in quotes, in 2015. They called it the Harris and Stockdale Megalithic Foot, or the HSMF for short, to distinguish it from other similar lengths. It is 14.142 inches, or 35.92 centimeters, or 1.1785 feet. The length of the diagonal of a 10-inch square. So in the next page, they have a diagram here of a square, 10 inches on a side, and showing the diagonal being 14.142 inches. In their analysis, they had surmised that the celestial time periods of the sun or moon might have been used in conjunction with the HSMF to design and build megalithic structures. Their first breakthrough came when they tested the lengths of the sides and the diagonals of the 4 station stones at Stonehenge. These form back-to-back, the ratio 13 to 12 to 5 Pythagorean triangles, which create a slightly distorted rectangle, possibly due to being used as indicators for partial rising or setting positions of the sun or moon. They tested it in association with the time period of the standstill moon, which is explained below in the article, which is 18.61 years. Harris and Stockdale used whole number lengths converted to HSMF, and the value of about 14.15 inches was found each time. Okay, so they have a diagram on the next page of Stonehenge and the, what were they called? The 4 station stones.
Oh, yeah.
Which form these 4 triangles or
a long rectangle. That you can draw an X through.
It's slightly screwed, yeah. Skewed. So they go and describe that. Basically, they're showing you in the diagram the distances in feet between the long sides and the short sides. And this is interesting. So when they measure the short sides, the average of the 2 short sides, they get roughly 109.6 feet.
Okay.
And then they say 5 times 18.61, which is 18.61 is the
standstill period or whatever.
That's the standstill period.
Yeah.
So 5 times 18.61 of their unit.
Okay.
Right? So they're using, it's kind of tricky. They're using the unit HSMF, which is the diagonal of a 10-inch square, 14.142 inches.
Okay.
So they're saying 18.61 of that unit.
Of those.
Right? So the 2 short sides, the average of the 2 short sides is 109.6 feet, which is 5 times 18.61 of the HSMF unit.
Okay.
And the error is 0.03%. The average of the 2 long sides is 262.7 feet, which is 12 times 18.61 of the HSMF unit. Error is 0.15%. And then the average of the diagonals of that rectangle at Stonehenge between the 4 station stones is 284.8 feet, which is 13 times 18.61 of the HSMF unit. And the error on that is 0.11%. So the result of these calculations tell us 3 things, they say in the article. 1, the HSMF unit of length was used in the creation of Stonehenge. 2, the time period of 18.61 years was known and used. And 3, the near perfect result was achieved despite the apparently intentional distortion of the rectangle, which they claimed earlier in the article was due to them wanting to set it to specific rises and settings of whatever.
So they had to distort it, and yet they still managed using averages
to get
these particular kinds of numbers using this unit of measurement.
2 tenths and even hundredths of a degree of percent of accuracy.
Okay.
So claim these guys, right?
And this unit is like a foot plus 2 inches, basically, just a little over, right?
Yeah.
Yeah. So it's a little longer than a foot.
Yeah, you make a 10-inch square and you take the measurement of the diagonal.
Right.
Which, you know, we've learned from Randall that this, I mean, even this unit of measurement, the inches and the foot and all that kind of stuff is possibly very, very ancient.
Right,
well.
yeah, absolutely.
And possibly based on Earth, like a sort of a mean, if you will, between man and the Earth.
Yeah, yep.
Which is kind of what they get into here. So the next section of the article is the lunar standstill, an explanation, which we might need a little more than what they provide. But it says the moon's orbit around the Earth is inclined at about 5 degrees to the ecliptic being the plane of the Earth's orbit around the sun. And then they have a diagram, and they're talking about the nodes shown in the diagram, basically saying that the moon's orbital plane processes, like wobbles in a way, slowly around, taking about 18.6 years. Thus, the declination of the moon varies from being about 5 degrees greater than that of the sun, and then 9 years later, 5 degrees less than the sun. When greater than the sun, each month, the moon will swing from being very high in the sky to low in the sky and then back again. At these times, the moon returns to almost exactly the same maximum declination, which changes very little for about a year or so, and it's called a standstill. The next standstill will be in 2024 25. So it's a lot like the solstices versus the equinoxes, right?
Mm-hmm.
So on the equinox, if you were to watch the sunrise on like days leading up to the equinox and then days following the equinox, you'll notice that the sun is rising in a very different spot.
Yeah, it's moving quickly.
It's moving quickly across the horizon at rising over the course of days.
Or setting, either way.
Rising or setting. And the equinox is really at a specific point in time where the sun could be up in the sky or even it could be nighttime. But basically the sun's motion throughout multiple days seems to be great along the horizon, whereas on the solstices, the sun appears to rise in the same position on the horizon multiple days in a row, up to 3 days.
Yeah,
right?
and as it's approaching or leaving the solstice, it's also moving much less.
Much less each day.
Right, that's right.
From the day before. So it, in a way, you could think of the solstices of the sunrise being the standstill of the sun.
Yeah, that's right.
And in the same sense, the lunar standstill is that orbital plane of the moon around the sun is wobbling, and when it's in line with the sun, when we have solar eclipses where the moon is actually in front of the sun, the next day it's way out. It's way far away from the sun, right? It's moving quickly, but then when it gets to the point of in a similar fashion as being the solstice, it's at a standstill where it seems to be rising, or its maximum declination, like its height in the sky, seems to be the same, or its rising position seems to be the same for multiple, up to, a year. Yeah, or two. It can be seeming to
So yeah,
be
by
same.
the wobble, like the way I think of it is if you take that ring that is the moon's orbit around the Earth, and then you just kind of roll it like think of like Kyle was saying earlier, a coin that you've spun and now it's slowing down. It's now rolling around its edge.
Yes.
Or a plate, that's rolling around its edge. That's the wobble of the orbit, and it's a very minute one, 5 degrees up or down.
5 degrees different than the ecliptic.
Yeah. Yep.
And so you can think of I'm sorry, I interrupted you.
No, that's good. You're right.
You can think of if the Earth is tilted at 23.5 degrees, the moon's orbital plane can be tilted in the same direction as the Earth's tilt compared to the ecliptic,
Which puts it at 18 something degrees.
Yeah. What is it? Well, we had that. There's actually a good Wikipedia article with a good diagram.
Yeah, on lunar standstill.
On the lunar standstill. Let's see.
Is it that one? No.
I don't know.
Yeah, it should be.
But anyway, it's either 5 degrees greater than the ecliptic or 5 degrees less.
Yeah, that's right.
So that tells you whether it's
Either
a major
add or subtract 5 degrees to the tilt of the Earth.
right. So that tells you whether it's a maximum or
Or
a
minimum lunar standstill. Yeah.
So anyways, it's just interesting. That cycle takes 18.6 years. And so they're claiming that this unit of measure being multiplied times 18.6. It's like says
a bunch of things. Like they knew about these inches, this imperial measurement system, that they were using this particular one of a 10-inch box that you draw the diagonal through, that was a ratio that they used. In other words, the bottom of the triangle that's made from that particular line, right, which you could view as a ratio. And then that they also knew about the lunar movements.
Right. And that's basically what they're saying. So so the next part of the article.
There it is. The watcher posted it. Yeah.
He posted the diagram. Yeah.
Yeah.
Yeah. Maximum declination, 28.5 degrees. Minimum declination. Wait. It says the same thing. There should be two different ones. But anyway, the next portion of the article is the origin of ancient units of length. And so the article states, in 1888, Penrose measured with great care the width of the Parthenon platform, finding it to be 101.34 feet, or 30.89 meters. This is almost exactly 100 Greek feet, which is 101.25 feet. The sexagesimal numerical system with 60 as its base, as opposed to the decimal with 10 at its base, was commonly used in antiquity. This is the reason for why there are 360 degrees in a circle, 60 seconds in a minute, and 60 minutes in an hour. 101.25. Oh, we out of time here?
Yeah.
Oh, well.
I was trying to give you a silent signal.
Well, let me just finish this. So 101.25 times 60 equals 6,075 feet. Or 1,851.66 meters. So just going back to the feet, 6,075 feet, they're saying in the article, the nautical mile is 6,076 feet. And is the length of 1 minute of arc of the Earth's polar circumference, i.e., an example, 1 minute of latitude.
Okay.
Therefore, we learn from this that the Greek foot has a geodetic origin, meaning that it is based on the dimensions of the Earth.
Okay.
And with that, we shall take a break.
That's right. Flying snakes.
Snickets. There's a lot of numbers in this article. I apologize. Numbers are hard when you're listening, but just bear with us. We're also, I mean, I'm looking at these numbers. It's still hard. But basically what the article is getting at is that 100 Greek feet times 60, so 6,000 Greek feet is very close to
a modern nautical mile.
The modern nautical mile, which is 6,075 normal feet.
Yeah.
And that length is 1 minute of arc of the Earth's polar circumference. And the watcher had just pointed out that that means that
the width of the platform of the Parthenon.
100 Greek feet, which is the width of the Parthenon, is basically the equivalent of an arc second.
Yeah.
Is that right, watcher?
That is absolutely correct.
Okay, so the writer of the article or the sources where the writer got this information are basically trying to establish that the Greek foot is geodetic.
And that they were familiar with the sexagesimal system.
And that it's, yeah, ultimately that it's based on the dimensions of the Earth.
Yeah.
Meaning that's what geodetic means. So...
Yeah.
So the article continues. There's a very useful book by A.E. Berriman, written in 1953, which has information on ancient units of length, weights, volume, and their origins. He details how nearly all of the units of length used in Greece, Rome, and Egypt had a geodetic origin, many of them being variations on other lengths. There is evidence for an advanced, very early society in the region of Mesopotamia, the Ubaid in Samaria, U-B-A-I-D.
Ubaid? I don't know.
Okay.
Let me see if I can find out.
The Ubaid in Samaria, which is circa 6,500 to 3,800 BC. The region was fertile owing to the regular flooding of the Tigris and the Euphrates. It seems likely that the dimensions of the Earth were known there. In principle, it is not difficult. So in here, the next section is they're going to describe how to do this, how to figure out the size of the Earth.
Okay, Ubaid is how this is said. Ubaid. And yeah, this is the source of the somewhat famous Ubaid figurines, the ones that look very very reptilian.
With the big eyes and
they have the huge eyes and the long snouts.
Yeah,
and
these carvings.
There's one, it's a female holding a reptilian-looking baby. Mm-hmm. She's breastfeeding it. Very strange-looking figurines. Those are from the Ubaid, I believe.
Okay, so continuing on here, it says, basically, to measure the dimensions of the Earth, you need to measure the angle of a bright star above the horizon when it is at its culmination or its maximum height or angle in the south. And to do this, you can use a plumb line and use water for level and an accurate scale on a large protractor. So basically, you're looking at the star when it's at its maximum height. You're using water as a level. You're using a plumb line as a vertical being plumb. And then you measure the angle of the star with an accurate protractor, which I don't know how you get one of those. But anyway, then you move north or south so that the angle of that star changes by a measurable amount, perhaps a degree of arc. And then you measure in some way the distance between the 2 points that you measured the angle of that star at its maximum.
So you unroll a string as you walk south.
Or you got a guy that has a real consistent pace. You have to make a straight line. So, yeah, it is simple, but it's probably difficult to actually achieve this, right? Without, I mean, how do you measure the distance?
And how do you walk a straight line? I mean, you can stand in one place like a surveyor and identify a point that's a straight line away from you.
You would have to survey this.
Yeah.
Yeah.
Because unless you have a completely clear and flat plane to walk on, you can't walk an actual straight line with no obstacles.
That's right. So you could get approximations.
Yeah. So I would say you'd have to survey each spot you wanted to get to.
Yeah.
So you'd have to send some dude running to the horizon, and then you're like, okay, that's a straight line from here to there. and then you go to that spot and then send him off again.
Yeah, it would be very hard to do
difficult.
this, to measure that distance. And then, you know, you'd have to include your changes in elevation. So, I mean, the article states that
I guess you could.
This is what they say. In principle, it is not difficult.
Right. Like, as a thought experiment, it's simple.
Now, if you had, let's say, like a body of water, like an inland sea or something,
Okay.
that you could use, right? So you can measure in knots or in however they would do it.
Yeah, and it's relatively flat.
It's flat. it's flat basically, but it's got the curvature of the Earth or whatever.
Yeah.
So that would be easier because you can't go in a straight line, and you could use the stars to navigate, but still measuring the distance.
Yeah. How do you measure the distance?
Yeah.
The other thing you could do is if you had some prominent high place to start from that you could always see as you went,
You can triangulate.
then you could, yeah.
Yeah. So it's doable, and it appears that they did this. However difficult.
I'm sure there's easier ways that we're not thinking of because we haven't tried this before. We should look it up. How would you do this?
Well, what they're saying is, you know, you move south or north or whatever so that the angle of that star changes by a measurable amount, perhaps a degree of
So you have to keep stopping and setting up your plumb and your water level and your protractor to see has the star moved an arc.
Yeah, yeah.
And
Well, you could do that with, you could test it in a less accurate way just to see like, okay, it hasn't moved very much. Let's keep
and
going.
you don't have much time.
Well, you'd have to do it days after.
Yeah, or you have to wait till the next year when the star is in the same spot again, right? Because you wait until it's the highest it's ever been, which is going to be only a day or two, right? Like that's going to change as the year continues, right? So that's where you get the highest spot, and then you travel some distance, and then you have to wait for that same day again the next year for that star.
I mean, technically, you could use whatever the North Star is at that time. Like
Yeah.
if it was Vega, and you knew the distance that Vega was away from the actual
yeah, okay,
pole.
that's true. So you could use an undying star.
Yeah. Yeah, you use an undying star. You use the Big Dipper, something there.
Could you reverse engineer all of the data out of tracking the sun and the moon and then raising stones in the places?
Well, I think he's using stars here, so the sun and the moon have their own relative motions.
Right. Well, I mean, like if Stonehenge, for example, if you tracked the movement from the center and then raised your stones as markers, you would create these internal distances just by tracking those movements, potentially.
No, because you have to move around.
This is to measure the Earth.
To measure how big the Earth is, you have to like leave the position that you measured that star and move around the circumference of the Earth
the disk.
some distance so that star is now a degree lower or some portion of a degree lower in arc or higher, depending on whether you go north or south.
And then using various types of triangulation and math, you can define the arc that you walked.
That's right.
On the circle that would give you the circumference of the
right.
Earth at that particular
like
latitude.
I went 60 miles and the star moved 1 degree in the sky.
Yeah.
And that'll tell you the curve that is the curvature of the Earth.
For the north to south curve. Like, in other words, it won't give you the equatorial, but it'll give you the
Right.
polar circumference.
But of course,
Yes, it
everybody
could also
knows it's a
be-
perfect sphere.
It's actually a disc.
Or you could just have one guy standing in one spot for 72 years.
We're measuring. We're not measuring that. That's a different measurement.
I think really, based on the parameters you guys are throwing out, it seems like one of the only ways that I can ever come to grips with divining this knowledge would be you'd have to have a preconceived notion of what you're looking for and then take consistent measurements over a period of time.
In order to do this, you would have to know, like,
You have to know what you're looking for before you're
That's what I'm
defining
trying to
what you're
say.
looking for.
That's what's interesting about it, is that if you have this idea, like, let's say you were a person who traveled a lot in ancient times, and say, well, I've been in this city, and I've actually measured the declination of the North Star, whatever the North Star was at the time, and it's this high.
Yeah.
And I've also been in this other city a long way away in some direction.
And
right?
I stayed there for months, and
Yeah,
the
and
North
I
Star
measured-
never went higher than this.
And I measured the North Star, and it was always this high.
Yeah.
And there's 2 different heights. So like, what's the deal? You know, so you could, I guess, you could arrive at this idea like, well, maybe the Earth is round because of that. I'm sure some astronomer could come up with this idea. Is that how it happened in the first place?
Yeah,
I don't know.
Because and then once you know that, you know, given any point on the circumference of any circle, if you can define any part of the arc away from that point, then you can use math to define basically the entire circumference of the circle.
Yeah, and it becomes a matter of like, how accurate are you at that point? Like you could get a ballpark figure by just going from one city to the next and
Right.
knowing like,
And
well, roughly it's like this far apart.
Yeah,
You get
and
a ballpark figure.
since you would think, mathematically speaking, that the Earth must not be since you're thinking about defining a circle by defining a point of like a section of its arc, then you would think, well, maybe this thing that I'm on is a sphere.
Exactly.
Right.
Yeah. Yeah.
And because the sphere's spinning, you can't do this in the other direction, right? It doesn't work to walk east or south or east or west. You have to walk north or south.
Yeah.
Because that north and south doesn't have, except for the yearly movement, doesn't have movement relative to the fixed stars in the background.
That's right.
So you have a limited amount of time to do this unless you unless you can get to the place where the fixed star that you're looking at has moved a degree of arc in the sky in a couple of days, then you have to wait till the next year to do it because it should change, right? Isn't that right? Or is it going to stay the same?
No, just for example, the North Star.
No, you're right. It'll
Like
stay the same.
each star of the undying stars just makes a circle in the sky. It's always, its maximum is always the same distance from the horizon, depending on your latitude.
Yeah, you're right. You're right. What I'm thinking is when you're looking past the sun, so that changes it.
Yeah.
Yeah. So they
So
shouldn't
then-
move north and south.
No.
If you have a reliable distance between your 2 points, you can triangulate and then from that project the rest of the dimensions of the orb.
Yeah.
Okay. Still, why
you're-
would you look for that if you didn't
You're
have
not-
some sort of notion?
I don't know if
Like,
this is triangulation. This is
No, you're using
measuring
a fixed point.
you're measuring the distance that you walked and how much the angle changed
Yeah.
from a fixed point away from that surface.
Yeah, you're using a fixed point in the
And assuming that angle or that change in angle is going to be consistent. Like the Earth's not banana shaped, right? Because if it was banana shaped, it would
greatly depend on where you were on the banana.
the angle that fixed point would change based on the distance that you moved.
Yeah.
So think of a hill like a perfectly round dome.
So
And on
there
one,
would be,
hold on a second. On one side of the dome is, let's say, a tower, right? You have like a cell phone tower, and there's this big dome between you and the cell phone tower. You're standing at the foot of the dome. You start walking up the dome, and the top of the cell phone tower,
Where you can see more and more of the
more
tower.
and more of the tower as you go over the dome. So if you measure the angle of the top of the tower from where you are standing on the dome, and then you back away from it, and the top of the tower seems to, like, you see less of the tower.
Yeah.
Then you measure the angle from this new position, and you know the distance that you walked. You can come up with the circumference of that dome if it was a whole sphere.
Yeah. Right.
but it still involves 3 lines and 3 angles, right? From the point of the tower over, like a triangle.
Yeah, you're just you're not able to determine the distance to the far point, which is what triangulation is usually used for. Yeah.
Right. You're using it
to determine the distance of the arc.
Of the arc that you're covering.
That's right.
How far you have to go? How far you have to go to change 1 degree of arc?
Yeah,
and from there you can multiply that times 360 and get the circumference. Okay,
the polar circumference.
Yeah, because
the equatorial circumference is not
changing all the time.
It's you can't use the fixed stars for that one because it's spinning. Yeah.
Dude.
Is this making sense? I hope this makes
It's making sense to me. Did we not turn this thing over?
No, we didn't.
The thing that blows me away though is like,
I understand what you're saying.
The advanced nature of this mathematics. 2, I'm willing to accept the possibility of somebody who's always watching the sky and like travels a lot, thinking, "Wait a minute, we must be a floating orb in a space sea of stars." Like it just there's the standard model seems to have a giant gap in things that the ancients probably had as base knowledge.
Well, you could
before doing a lot of stuff.
Yeah,
that's what becomes ever more apparent to me with this.
Your model of the universe doesn't have to be as complex as ours is now for this to work. Like you could think, for example, that, you know, how they used to call it the spheres, right? So you could think that the wanderers, the planets, are in their own sphere, maybe part with the sun and the moon, or maybe those have their own separate spheres, and then the distant fixed stars are just another outer sphere. It isn't necessarily that far away, but they don't move.
Definitely.
Yeah.
But like our standard model of history says that Columbus thought he was going to fall off the side of the world, and that all the maps have there be dragons at the edge. Like, I mean, it's just, it becomes ever more ridiculous to me. Some of the presupposed components of the model, I guess, is just the way to say it.
So one thing that jumps out at me here is that the nautical mile, going back to the nautical mile being 6,076 feet, that's the length of 1 minute of arc of the Earth's polar circumference. Meaning, and the article later states, like meaning that 60 nautical miles is a degree of arc.
Is it a minute?
Right?
You'd have to go
6,775 feet is 1 nautical mile, and that's 1 minute of arc.
So a minute of arc would be 60 times that, right? I mean, a full arc degree.
Yeah, 60 nautical miles.
Okay, yes, yeah, okay, that's what you said.
Is a degree of arc.
Yeah, so 60 nautical miles.
And that's what they say, like I'm
sorry, I missed that you said that. Yeah,
in their description here, when they're saying like the guy in ancient times who's trying to figure out to measure the Earth, he moves a distance until the star changes 1 degree of arc. Let's call it 60 miles. That's what the article says. Call it 60 miles.
Yeah.
That's just cool. So we need to switch to the nautical mile, folks.
Yeah. So that would be
6,076 feet.
300. It's 6,076, right?
Yeah.
It's 364,560 feet would move a star
1 degree
of arc in the sky.
Yeah.
And so if you can convert that to the pace, and you have a relatively regular pace, you could roughly count it and get a pretty good, you know, it wouldn't be super accurate.
Yeah, just divide that by 1,000. Right? Or no, a mile is 1,000 paces. 5,280.
Yeah, so how many feet is 1 pace is the question.
Yeah, it's about 5.28 feet.
Okay.
That's because
so divided by 5.28. So in about 69,000 paces, if you can make yourself walk a straight line. Like, so if you had your compass, you just followed it north without deviating. 69,000 paces.
Yeah.
That'd be tough. I like your story. I think that's more accurate, that some astronomer would notice that, like, when I'm in this city, this star that I look at is at this angle, and I'm in this other city, it's really close to a degree off of that.
Yeah.
You know, and maybe close enough to where he could be like, so if I was in the outskirts of that city, maybe it would be exactly a degree. And then if he would know the distance between those two cities, if he could find some way to measure that.
Yeah.
Which he wouldn't be able to do with a road or whatever.
It just wouldn't be real accurate, right? It would be they would be these.
There would be inaccuracies for sure.
There would be
but
these,
that would
like,
that would give you the clue to then talk to your colleagues and say, how can we do this incredibly accurately?
Yes.
Let's get a couple of ship captains on the sea, and get them exactly, north and south of each other.
Yep.
Drop anchor and do some measurements.
Yeah. That's cool.
Of course, then the ship is going up and down and side to side. You can't do it.
Well, you'd have to have a glassy sea.
You have to wait. You have to do it on a calm lake.
So, continuing on, the article states, the writers of the article state that, in fact, which I don't know if they should say that, but it is probable that most, if not all, ancient measurements were ultimately based on the dimensions of the Earth. This includes the meter. The Earth's meridional circumference is 40,009 kilometers. In other words, the meridional circumference is the polar circumference, which I did not realize until I read this. So now they're moving on. They're saying tracking the spread of the HSMF unit of length. It is not known by what route the inch was developed, but it was known in Samaria. Berriman, some guy, discusses an ancient measure.
That's the guy who wrote the book.
That's right. He wrote the book. He discusses an ancient measure, the Sumerian foot, of 13.2 inches, or 1.1 feet, or 33.43 centimeters. This became the unit of measure for the North German tribes in Roman times. When the Romans left Britain, the Saxons, one of the North German tribes, came to Britain, bringing with them the Saxon foot. This became the standard unit of length until one of the medieval kings, probably King Edward I, changed its length from 13.2 to 12 inches. So we use a length that has an ancient origin. In another, more direct way, the Sumerian foot is still with us. The rod, or perch, a length of 16.5 feet, is still used by surveyors. It is 15 times the Sumerian foot and 14 times the HSMF. It's interesting.
I don't catch what's interesting. I've got distracted.
Well, the HSMF being the unit of measure these guys are proposing.
Got that part. Yep.
And they're just saying that this ancient Sumerian foot is still used by surveyors, and it's called the rod or the perch. And its length is 16.5 feet. It's 15 times the Sumerian foot, or 14 times HSMF. So these are like whole number multiplications of these.
All right, yeah.
Of these units.
I did know about the rod because we had to look that up. We were on with Soraya the other night. Remember we were reading that article about they found the person like 25 rods away from the road or something? Yeah. It's 16 and a half feet.
Yeah, so I think that in other words, perhaps it's significant. Like if you were looking at this and you're comparing it to all these megalithic sites and you're seeing that it is represented over and over in whole number multiplications, right?
Yeah.
Or a multiplication like the length of time of the maximum and minimum lunar standstill. Yeah, you're seeing some kind of correlation there. Now,
so either whole numbers or some like known astronomical cycle.
Yeah.
Yeah.
In terms of years.
Yes. Yeah.
That's what they're finding interesting.
Okay. I agree.
It gets complicated, like I said. It's like,
what did that say about them bringing the Saxon foot?
Basically that the Sumerian foot was 13.2 inches. And then that became the unit of measure of the North German tribes in Roman times. But then the Romans left Britain
and brought the Saxon foot with them when they left.
They brought the Saxon foot when they came to Britain. They brought this. When the German tribes came to Britain, they brought the Saxon foot.
Okay,
and then some king, Edward I, changed its length from 13.2 to 12 inches.
Okay.
So he changed its length for some reason. The foot was too big.
We could use the Saxon foot. Of course. Brother Maynard carries it with him.
So yeah, it's just, surveyors are still using the original 13.2 inch foot.
Okay.
In the rod, which is 15 times that 13.2 inches.
Okay.
Right? Is that correct? I think so. The rod is 15 times the Sumerian foot and 14 times the HSMF.
Okay.
So the article continues. The HSMF traveled east and was used in the construction of the Great Bath of Mohenjo-Daro in the 3rd millennium BC, located in modern-day Pakistan. Precisely made bricks were used. According to Berriman, the mean length is 471.5 inches, which suggests bricks of 4.714 inches, 1/3 of the HSMF.
All right.
So then they have what?
Break time. Right on the dot.
All right. All right. We'll take a break.
Yeah.
We'll get into. We'll have to look into that. All right. We'll be right back.
Yeah. And we are back, ladies and gentlemen. The second half of the show. Brothers of the Serpent podcast. So yeah, I didn't, I meant to say this at the beginning, but because I'm leaving next week and it's kind of last minute, sort of, I wasn't ready with more Fortean stuff with the book. Maybe you did say that. Is that what, did you say it? Anyway, the book report's not over. We're just taking a break because I'm leaving for a week and we're going through this excellent article that Kyle found on ancient origins.
Totally winging it. Was planning on doing a Patreon episode of this article, but well, here we're just doing it.
Yeah.
Doing a deep dive into it.
This is what happens when Russ leaves things to the last minute. He shouldn't do that.
I didn't leave them.
I dive in to save the day.
It wasn't me.
This is what it would be like, folks, if I ran this show.
Be disjointed, like, wait, let me see what it said. I don't remember.
Yes, he actually printed it out, which is cool. He's using real paper.
Yeah.
And no, it wasn't me that left it at the last minute. It was Randall.
Oh, dude. I'm totally sure that that's
Completely blame it on Randall.
absolutely true.
If they would have had it planned out months and months in advance, I would have left it at the last minute. But that's
No, you
not what
probably
happened.
you just would have told Laura and she would have handled it.
No,
way in
I would have
advance.
left it at the last minute. What happened, though, is that they left it to the last minute. So now I'm just doing my normal planning.
That's
Which is
fair
at the
enough.
last month, which is at the last minute, yeah.
Dude, I've never had anybody sell an Airbnb out from under me.
She took one look at Russ's name and was like, nope.
Nope.
Looked him up, saw the podcast, was like, no.
No way.
Not happening. It's the first filter. It comes back on you in many, many ways.
Many ways. That's right.
All right, so moving on with the article on ancient-origins.com. Name of the article is A Rediscovered Unit of Length and Implications for the Neolithic. We are doing a deconstruction of this article as best we can on the fly here. And they were describing their unit of length, which is the HSMF. It's a terrible name for this unit. We should just call it the HSMF. the HSMF.
Husmuff.
Man, there's just no good way to do this. Anyway, it's 4 names in an acronym. Terrible name for this thing. And they're describing that basically they're going through all these ancient sites and showing how either in whole numbers this unit works out, or like in whole number multiplications, or in whole number multiplications of a significant astronomical length of time, like 18.6, this unit fits into these geometric constructions perfectly.
Just call it the MF.
And the MF.
How many months?
That's only the last guy's name.
I can't watch it. It's the holy shit. I can't even say it. This is a family show.
Mother flippin'.
The holy crap, mother flipping foot.
Holy shoot, mother flipping foot.
Holy shoot. So they're pointing out the Mohenjo-Daro bath, the Great Bath. The bricks were made, basically each brick was made precisely to be 1/3 of this unit.
Okay.
4.714 inches, 1/3 of the the holy MFer foot. And then they give, okay, so they go on to the next thing. There's a diagram here again we'll get into. It says, during the early civilization in the Ubaid period in Mesopotamia, many buildings, including temples, were built, and the foundations and the lower parts of the walls of some of these still exist, dating back to the 5th millennium BC. Grids drawn on tracing paper were overlaid on plans of the temples. It was found that the grid of 72 centimeters was the one that fitted closely in nearly all cases. In other words, closely to the foundation, like fit perfectly into the foundation, overlaid onto the foundation. Kuba, which is someone's name probably who wrote in 1990, claims that the close fit is self-evident. And the article states, keep in mind that 72 centimeters is almost exactly 2 times the holy shit MF in foot.
28.346 inches.
It's a difference of only 0.16 centimeters. It's that close.
Wow.
72 centimeters, 2 times this new foot.
So even there, it's fitting some kind of strange processional.
That is cool. Yeah. Including the metric system.
Now you're dragging the metric system.
Number in the metric system.
Yeah.
Interesting. So, yeah. So 36 centimeters would be roughly 1 of these feet. Right? Yeah. So the HSMF, I gotta figure out how to say this foot, was used in China and was known as the Kung Chi. I think I'm pronouncing that wrong. A length equal to 1/2 of the Kung Chi, 7.07 inches, was also in use. Confucius was 9.6 of the standard Chi and was considered to be tall. Okay, 9.6, and that's how tall he was. Moving across the globe, it is not certain by what route the HSMF reached Britain, but a recent paper by Schultz-Paulson in 2019 suggests that lengths may have traveled west through the Mediterranean and then north up the Iberian Peninsula. The HSMF in Britain and Northern Europe. It is believed that nearly all the stone rings in Britain were built between 3000 and 1500 BC. Alexander Thom, who was a very able mathematician and engineer, measured the dimensions of several hundred stone rings or stone circles. The book Bar 81, written in 1984, contains drawings and information for most of them. The dimensions of each stone circle, usually given in Thom MY 2.722 feet. This is strangely written. And or feet. I guess Thom MY is a unit of measure.
I'll check.
They were converted to the HSMF. An analysis was begun using basic Excel tables. The row headings and analysis of one site in the table was as follows. And so we have a table here showing all the ring diameters and the perimeters, comparing the thom versus feet, and then the HSMF and all that kind of stuff. So they're just comparing all that. So in explanation, on each row, the HSMF diameter and perimeter was divided by 18.61. Again, that's the lunar standstill, the length of time of the complete cycle of the maximum and minimum lunar standstill, 18.61 years. So the HSMF diameter and perimeter was divided by 18.61. Also 27.55 and 29.53. But then they were divided into 346.62. I don't even know why they're doing this. 365.25.
Okay.
Okay, so these are
Days of the
obviously
year.
that's the days of the year. In most cases, this leads to values greater than unity. The 5 values are examined for values close to an integer. So again, they're trying to find whole
numbers.
representations of this foot.
So, real quick interjection, Thom, that's the megalithic yard, which is 2.72
yes.
feet.
MY, the megalithic yard. That's right.
Okay.
So in the above example, a multiple of 4 for 27.55 is indicated. Let's
So
see
why
what
did
he's
they list
kinda
these
getting
other
to.
numbers? It was on each row, the HSMF diameter and perimeter was divided by 18.61. And then what are these two? 2755 and
I think that might be the
2953.
megalithic yard.
Oh, okay. And then they were divided into these two, 346.62 and 365.25.
Yeah, they don't explain that yet. They
Yeah.
might explain
Okay, maybe they'll explain it later. All
I'm
right.
not sure. So there's these numbers that we don't know what they are. If I had studied this article before starting the show, we probably would know. So they're basically just go on to say they're talking about the accuracies comparing to these. So the 5-row headings were used. The standstill period, 18.61 years. The anomalistic moon, 27.55 days. The synodic month, 29.53 days. The eclipse year, 346.62 days. And the calendar year. So
Okay.
these guys are looking for these astronomical periods.
Okay.
And like trying to fit this HSMF foot. The initial investigations seem to show that in true rings or circles, stone circles, the diameter or perimeter was a simple multiple of the period of the anomalistic moon or the eclipse period more often than would be expected by chance. Computerized analysis was required, and so I approached Victor Reyes, a computational specialist in archaeoastronomy whom I had met at several SEAC conferences. I sent to him the relevant details of the rings, or stone circles. There were 62 true circles and 42 others. For an example, flattened circles or egg-shaped circles. Or rings, they're calling them. The 62 true rings, having only one value for each of the diameter and perimeter, were used for analysis. Any unit length could be entered, and the table and output was automatically updated. The ratios tested were for the integers 1 through 10 only. The colors, okay, so they're basically, this is what they're describing how they did the analysis of like all these stone circles and comparing them to all these different astronomical cycles. So they show in a diagram I think this is the accuracy hit codes, which they're calling them, for the ranges of, and then the error is shown. Let's see, going on. Like they got this huge table here of all these different stone rings that they measured and where they hit in some type of multiple of the HSMF.
Okay.
So in explanation, they say part only of a table for analysis. Let's see. Let me check this real quick. As explained earlier, the dimension in HSMF is divided by the period 18.61, 27.55, or 29.53, but into 346.62 or 365.25. So those astronomical periods.
Yeah.
The 5 columns of figures are automatically revised for each of the 4 error ranges, blah, blah, blah. They go on.
Yeah, so that's just explaining how they've positioned the data in the table above.
Yeah.
Yeah.
Let's see. Let me get to the meat here. Okay, so they're saying the scores for 27.55, which was the anomalistic moon period, and 346.62, which was
the ecliptic year.
The eclipse year.
Eclipse year, yeah.
Where was I? Strongly associated with the HSMF.
Okay.
So it's like that unit was used for those two predominantly. The analysis was checked by 3 independent statistical analysts. and none of the other 3-period values registered as being associated with the HSMF. So the association of 18.61 was using the pair of Stonehenge triangles, not stone circles. All right, moving on. Sorry about that. With the exception of the solar year. Wait, is this right? Yeah. Yeah, okay.
Yep.
With the exception of the solar year of 365.25 days, each of the other 4 values tested to have periods which vary about a mean, meaning an average. In order to determine the mean period, records would have to be kept for many cycles. Lunar eclipses have a mean period of 173.3 days. Since in some years there can be 3 eclipses and others none at all, this would be difficult to determine. And then they have a graph showing like the different cycles of this. The variation of the anomalistic moon period is considerable, varying as it does by up to nearly 3 days. When a diagram is available, then a pattern is seen, but to have determined the mean of 27.55 days, as was done in prehistory, is very impressive. We do not know if the determination of the period was done in Britain or elsewhere, but it was built into a significant number of megalithic stone circles in the Neolithic. The earlier Z-score analysis showed that the 27.55 and 346.62 were used in the construction of many true stone rings. These rings were planned, and for whatever reason, these values recorded in them.
So what they're pointing out here with that, which is that last one you were talking about, was the
anomalistic moon.
Yeah, and then the eclipse
year.
They're basically saying that both of these things, in terms of a mean number, an average, is very difficult
hard to
determine because it can vary massively from year to year. You can have 3 eclipses in one year and then none.
Right, so you need
others.
a long period. You need
a long period of observation and calculation to find out. That's the thing.
The average is. Yeah.
What if you could calculate it?
Yeah. Yeah.
This is assuming observation is the only way they can know, right?
Right, but if they had other knowledge, right?
Yes. If they were able to just calculate
do what we do today,
right?
Which is like, okay, we know all these motions, we know basically what the angles are, we know the wobbles, and we know these long cycles, and let's put them all together and figure out what they average.
Right. We don't have to observe eclipses to get an average, a mean, because we can just do calculations. But on the other hand, there are ancient accounts of eclipses that our calculations don't account for.
That's right. That's right. So they go on to say the eclipse year of 346.62 days is a large number, and only one stone ring records it as a diameter, which is Sanctuary A, 345.7 HSMF.
Oh, yeah.
Their unit.
That's really big.
Yeah. It is common as a simple fraction. Thus, there are 4 rings known where either the perimeter or the diameter is 288.4 to 288.7 HSMF, which is basically what they're saying is 346.62 divided by 1.2. Okay, because they're the foot, I guess. I don't know.
And 1.2 is what did you say it was, Watcher? The ratio of...
So that's the ratio of nautical miles to get 360 full degrees around, and the number of years in the years in the great year. So if you take 72 times 360 and 60 times 360, they have a precise ratio to each other of 1.2.
Wow.
I don't know if that's what they were using or where they got that original, motivation to use 1.2. But it's really interesting that I found it and just kind of went, I wonder if that matters. And now they're dividing by 1.2.
Yeah.
That's interesting. Yeah, maybe they go on to explain the 1.2 connection in the article. I don't know.
Okay.
I mean, there's so much stuff in here. They go on to describe the two large rings, the diameters of the two large rings of Brodgar, Orkney, and the Great Circle at Newgrange,
the Ring of
Ireland,
Brodgar.
are 288.5 and 288.4 HSMF. Multiply that times 1.2, and you get 346.62, which is the number of days in the eclipse year.
Okay. So yeah, that may be relevant then. So earlier what we were talking about, the 60 miles equaling 1 degree, that is, if you take that times 1.2, 60 times 1.2 gives you 72, which is the number of years it takes for the
precession to move the background stars 1 degree of arc.
Yeah.
To arc.
So your nautical miles to precessional degrees is a ratio of 1.2.
Or just the base of the sexagesimal system times 1.2 is 72. So that gives you here's our measurement system, and this gets into the time system.
Huh. Okay. So they go on to describe that other ratios, such as 1.25, 1.333, 1.667, 2, 4, 5, and 6 are known. Multiples of 1, 2, 2.5, 3, and 4 are usually used with 27.55, which is the
that's the
anomalistic lunar thing.
Anomalistic moon.
These ratios of used with the 27.55 have been used for diameters in these stone circles. So now they move on to the Thom megalithic yard of 2.72 feet.
I wonder if that's just Tom. Could be Tom.
Tom? Maybe, yeah, Tom.
I don't know.
So the unit was used in a limited manner for some rings and was used at the stone complex of Carnac in Brittany. The rings of dimensions close to 288.85 HSMF discussed earlier are given in Tom's work as 125 megalithic yards. This can be explained as follows, and then they have this I don't know what this diagram is.
Yeah, I was looking at
lots of math. It says this may look complex, but triangles make the transition simple.
Lies.
Yeah, I know. There's another diagram here of complex triangles. Well, they describe it in a diagram, which I'm not going to try to explain. But so they say, since there is no evidence for the use of the megalithic yard other than in Europe, and the HSMF appears to predate the megalithic yard, it is suggested that the megalithic yard is derived from the HSMF.
Okay.
Because they've found it in multiple places all over the world.
Right.
Another diagram of Stonehenge, Sarsen Circle, using the HSMF in its construction. They say both Flinders Petrie and Tom obtained values for the inner diameter close to 97.4 feet. And 97.4 feet is 82.65 HSMF, which is 3 times 27.55.
Ah. Okay, so it's 3 times the anomalistic moon thing.
Yes. Yeah, so in other words, the number of that diameter in the HSMF is equivalent to 3 times that astronomical cycle.
Yeah.
In terms of years.
Okay.
Lintels, as measured by Richard Atkinson, 3.5 feet by 10.5 feet. 3 HSMF equals 3.54 feet. 9 times HSMF equals 10.6 feet. So they're just showing that the lintel, that the actual measurements of the lintel stones themselves are extremely close to whole numbers of the HSMF.
Yeah.
Like they were cutting the stones to that number too.
Right.
3 by
3
9.
in this way and 9 by 9 that way. Yeah.
And 9 being the cube or square of 3.
Yeah.
Yeah. Outer diameter, 104.4 feet, or 88.65 HSMF. 3 times 29.53 equals 88.59.
And 29 point, that's the mean month.
Where did I put that?
That's the average days in a month or something. Wasn't that what that was? What did they call it?
29.53. Wait, where is it? I had it up here. Well, I lost it.
Yeah, I thought it was on this page.
Yeah, me too. Anyway,
I'll look for it.
That out.
Yeah, the synodic month, 29.53 days.
Can you
So we
look
should
that up?
find out what that is. Synodic, SYNODIC month.
And then they go on to say the inner and outer circumferences of the Stonehenge Sarsen circle are both simple ratios of the eclipse period, all lengths in HSMF. So the eclipse period again being 343 something, right?
The synodic month is another term for the lunar month.
Oh, the lunar
Okay.
month. Okay, of course. Yeah, so the 346.62. So they're saying the inner and outer circumferences of the Stonehenge Sarsen circle are both simple ratios of the eclipse period.
Okay.
And they lay all that out. More diagrams. Good grief. It just goes on. Okay, so they say Archie Tom, Alexander Tom's son, measured rings in Scandinavia in 1980. One of these was an ellipse. In the image, the ellipse is constructed on a 3-4-5 Pythagorean triangle. He expressed surprise on finding that the unit of length was 4.71 feet, which I think, if we go back, was a third of the HSMF, right? That's what the bricks were made. The bricks of the
4.71 feet is a multiple. It has to be a multiple because it's only 14 inches.
Oh, that's right. What was the 4.71? Anyway, getting lost here. So they're saying from 4.71 inches. Yeah, is a third
Okay.
of the HSMF.
Okay.
Anyway,
So
I
they're
don't know.
saying that that's referencing a third of the HSMF, but using feet. Is that the idea?
Yeah, I don't know. I'd have to. It's because they're using all these diagrams.
Yeah.
I'm not sure because they've got. I see that number repeated over and over again. 4.71, and that was, I'm pretty sure, the size of the bricks of that other thing.
Yeah, and so it's 1/3 of the HSMF if it's 4.71 inches.
Yeah. Yeah, I don't know. I'll have to-
But they're saying that if you just take the unit away from 4.71, you can use it as a ratio. So 5 times it or 4 times it or 3 times it, like they've got here, gives you all these values in inches, right?
I see. Yeah.
And there's one. 5 times 4.71 feet is 23.55 feet, 23.55 being one of these other numbers.
It breaks down to roughly 4 even HSMFs at
Okay.
4.71 feet.
Okay.
Oh, it's 4 of them.
4 of them.
Okay. Yeah, that's weird. That
Yeah.
4.71 inches is a third of it.
Yeah. That is weird. And 4.71 feet is 4 of them. Is
Yeah.
that right?
Yeah.
Okay.
All right, so I'm getting here. This is the end here. One last diagram, and then they say Peter Harris and Norman Stockdale examined rock carvings for possible evidence. They deduced a possible length of 1/56th of the HSMF and tested it on rock carvings. It gave positive results. The HSMI, which is the Harris and Stockdale megalithic inch.
Okay.
Is 0.2525 inches, or 0.6414 centimeters. Rubbings were made of a number of rock carvings which had cup marks. And I guess they show a diagram here of the... Yeah, I'm not really sure. And it's in strangely.
So they have a megalithic inch for this megalithic foot.
Yeah. And then there's one diagram that seems to be... Okay, this is called the swastika stone on Ilkley Moor in Britain. That's what that diagram is, I guess.
Okay.
It's on a nearly flat slab in... What is that word? Ilkley
No
Moor?
one knows.
The square outlines have been superimposed on a scale copying of the rubbing. The four sides of each square were measured to the nearest 0.1 millimeters, summed and converted to HSMI. The inner square is 81.7 HSMI, which is, and then they're showing that 3 times 27.55 is 82.65, so it's close.
The idea being that people may have made some of these carvings using a fraction of this megalithic foot that they have.
Yeah.
An inch version of it.
Yeah.
Based on it.
And so the last bit here is I guess this is a summary here. What does the HSMF mean when analyzing knowledge and ability in the Neolithic? 1. The HSMF is of length 14.142 inches, or 1.1785 feet. 2. It probably originated in Mesopotamia more than 7,000 years ago. 3. Megalithic structures, especially true stone rings, were built using the HSMF in combination with celestial time periods. Analysis has shown that time periods 27.55 days, the anomalistic moon, and 346.62 days, which is the eclipse year, were favored. 4. Determining the mean time periods of these cycles would have required extended observation and record keeping. The above history of measurement in units of length indicates much greater ability and knowledge in the Neolithic than is currently accepted. And then they finish by saying, this article summarizes some of the descriptions and workings included in A New Dimension to Ancient Measures by Dr. Thomas Goh and Peter Harris, and which is available on Amazon.
Oh, okay. So they've written a book about it.
Yeah. So... yeah, that's that. Lots of diagrams and stuff. It's just really cool. I love that kind of stuff.
Yeah, I'll put the link to the article in the show notes so people can go see the
Yeah.
diagrams and stuff too, for sure.
Yeah.
And it is break time. Should we take a break and come back and...
Yeah, for sure.
Okay.
We're back, ladies and gentlemen. Final segment of the final hour, and I'm done going through this article that I hardly understood the very end of at all. But yeah, I find this stuff really interesting. I love the idea of the geodetic measurement system in whatever form that it comes in, and I think it's cool that, like, you know, we still, like, when we're creating measurement systems, we try to base them off of something, you know, fundamental in the universe, right? And this is not something that would be clear to anybody looking at, like, when you're just looking at a structure or even a modern building, like people don't really think, it doesn't immediately make you think like, wow, I wonder what the measurement system was used to create this structure.
Mm-hmm.
But we live in a time where these things have been established,
Yeah.
and normalized basically across the entire society for a very long time. So it's not something that we're required to really think about. But then we have the metric system, which is considered the most modern development of a system of measurement, which is based on more fundamental things that we understand in physics.
But it's also interesting because you can think about it a little bit and think like in ancient times, if you're, you're just a farmer and your job, you don't particularly cut and make planks of wood for stuff, right? That's not, you're a farmer, but you need some planks of wood. So you go to the guy who does that and you're like, hey, I need some planks of wood. And the guy's like, well, how long do you want them? And you're like, like what do you tell him? Like nowadays you're like, well, I had 12 feet.
Yeah, exactly.
Right? I need 3 meters or whatever.
Yeah.
But back then you're like,
I want them 1 tree long.
See my leg? 4 of those.
Yeah, exactly.
So you can see how very quickly you would start thinking to yourself, it'd be nice to have a standard.
Yes.
But then the people who are coming up with the standards, the scholars or the thinkers or whatever, are thinking, I need a standard to base my standard on that's unchanging.
That's right.
And one of the things you would think is, relatively speaking, unchanging is the thing you live on relative to the stuff you see in the sky, because that stuff doesn't change. It moves around, but you're like, well...
Yeah, see, that's a big leap to me. I would think that, like, the way I imagine it is that the standard first becomes ourselves. Right? Well, how far is 2 steps for me?
But all you have to do is look around and see that people are drastically different. So that's not a good standard.
Yeah.
Unless you have a standard guy whose job it is, he wears the yellow suit with the black lines on it, and his job is just to be the standard.
But you're already talking about somebody who's cutting and milling boards.
Yeah.
Right? You're moved down the development of technology quite a ways from the beginning, which is like, well, how far have we gone?
Yeah.
When let's say you're like, it's tribal.
Well, we went 1,000 Krug paces.
So the thing that really strikes me about this whole thing is we have standard measurement today because, we have global communication, right? We have a way to standardize it. One of the implications of this is if you're the guy cutting those planks of wood, that every other guy cutting planks of wood knows this celestial standard measurement, knows how to figure it, knows roughly what it is, and then you go, okay, and cut the wood.
Yeah.
In order for it to be a standardized thing, it means there's someone in every location pretty much, within reason geographically who knows how to figure that shit out.
Yeah. That's right.
Or they have a cut piece that they use that was given to them, but it's taken because it can be figured out anywhere on the globe, and then everybody knows, which is just staggering.
Yeah, you're right. So it's like any mill in the world knows that as long as they use particular standards, that any other mill or construction company or even just the Johnson on the job has tools that will measure it in the same standard. Whereas maybe a long time ago, where I'm talking about, where you've got some kind of agricultural community. It's 7,000 years ago, Jericho area, whatever, in the Middle East, somewhere in in Mesopotamia. Maybe you have a local standard. But what's interesting, work like this that's being shown in these articles, is that even those what you would think of as a local standard nevertheless seems to have been more than local and also based on the planet.
Yeah, all relate to the holy shoot mother flipping foot.
Yeah. Or it could be that because somehow most of the standards that were developed and adopted by most of the civilizations used some type of geodetic measurement. And so they all will naturally have some kind of relationship to each other.
Yeah.
You know what I mean? Mm-hmm. So it's like,
so like everybody comes to the conclusion that we should use the planet as a base, as a base for our standard.
In some way. And that's where in the beginning of the article, when it describes it like, well, they apparently measured the Earth, and this seems like a ridiculously complicated thing to do, but it's in principle, it's simple.
Yeah.
Which it's like, yeah, and then you go into describing how to do that, and it's like, well, yeah, in principle, it's simple.
Yeah, let me throw a bunch of problems
into action. It's really hard.
That's right.
But
in principle, it's easy.
It suggests that this was done multiple times by multiple different civilizations. So they had, and maybe Randall, I bet Randall.
But why would they choose those particular, like why would they choose the ecliptic year and the anomalous moon? Maybe those are like much more visibly easy to measure. Like I was wondering about that when you're reading it. Like there's all these things they could have chosen, but there are these two that they seem to have chosen, the synodic month, or whatever, that seem to be related a bunch of times. And I'm like, I wonder if those things are, when you're just...
That's what's interesting, because those are like used as multiples.
Yeah.
Like let's multiply our unit of measure
by this, or divide it into this one.
Yeah, by some other astronomical phenomenon.
Yeah.
Which,
and I'm just wondering why they chose those particular ones out of all the ones you could choose. Like why not? Why didn't they use 365.25 more often? Instead they used the 3, 4, whatever, the the eclipse year.
Yeah, that's...
So maybe they were just, it was lunar.
It's in a way, it's incorporating knowledge of the cycles of the Earth into the building.
Yeah.
Which is like, that's kind of where the idea of...
But both of them are lunar. One of them is about lunar eclipses, and the other one is about the lunar month.
Yeah. Well, if you just use the year, right, it can tell you about the year, but it doesn't, I guess. Like
yeah.
These more like something like a lunar or a solar eclipse or a lunar eclipse is something that
it's more descriptive.
Like a lunar eclipse, you're going to witness multiple times. Mm. A solar eclipse, you're going to witness less often. But both of those occurrences are very startling to somebody who doesn't have knowledge of the Earth. Whereas, like, you might notice that, it's easy to notice that the seasons repeat themselves over and over.
Everyone will notice that.
Everybody notices that.
Yeah.
So it's like embedding a deeper knowledge of that these things are cycles.
But there's also the implication that the ancients wanted to, because what we end up talking about are standards for measuring in our three-dimensional space.
Yeah.
And yet they continuously include the time dimension.
I love that.
That's great.
That's
yeah.
so
So it's like they view the universe in this fourth dimensional way.
In this cyclical way.
Yeah.
That's what's I just think that's so cool.
Well, like we have 3 dimensions, and all of those are basically straight infinite lines.
Yeah.
But then there's this other one that we also interact with, but it goes in circles.
Yeah, and the only way to measure it is to pay attention to, like, you have these cycles that are happening obviously every day.
Yeah.
And then there's a slightly larger one that's maybe more subtle, and then there's a larger one that's even more subtle, and a larger one that's even more subtle, and then a larger one that's like obvious.
Yeah. Right.
It's really weird.
Yes.
Yeah. 18.6 years is not an obvious cycle.
No.
Unless you're really paying attention.
No, yeah.
So it's cool that they, yes, I find that fascinating that, because before I learned about any of these connections between the time and distance,
yeah,
the units of measure, I would never have thought of connecting a unit of measure of distance into time, or incorporating
which is why it's interesting, because physics, like space-time, this modern physics, this is what Einstein does, right? So relativity does this. It says that these things are intrinsically linked.
Right.
And that a light year, which is a measurement of time on one hand, is also a perfect measurement of distance based on a standard of velocity.
Right.
Right. So that right there, like, is really interesting because we think this is a new idea, and yet what it does is what the ancients have been doing for forever. It's harmonizing distance and time.
Yeah.
Yeah, and showing that they're intimately connected.
Yeah, that's really cool.
I don't know if I was in charge of coming up with a unit of measure that would ever happen.
Because you would be restricted to thinking of distance only. Is that
Yeah,
what you
but
mean?
it's almost like you need to start from ground zero. Like you need to start with nothing,
Yeah.
and then the idea of a distance measurement
Yeah.
and needing to have it be very precise. Well, how do I make it precise and standardize it to where I can get it somewhere later from nothing?
Yeah.
That's when you have to start looking at thing and say, well, what is the same?
Yeah.
You know, what, like you were pointing out, these scholars would realize that, like, well, what can we say that is the same? You know, that we could get the same measurement over and over again when we do this. Like
Yeah. We need something that doesn't change to base it on.
Right. So that's where you end up with astronomers like, oh, hey, you know, they're hanging out in the bar.
Yeah.
Right? And the astronomer's like, oh, I know something that doesn't
Yeah.
change. It's just pretty much the same all the time. Well, I mean, every time you look at it at this one particular time, it's the same.
Yeah.
And so that's, you know, you can see where they.
Well, and you can see other things too that people do. Like, how often have you asked somebody, well, how far away is that? And they're like, oh, it's about an hour, which is not a measurement of distance. It's about an hour away. You know, you're like, but I asked you how far.
Yeah, am I going 70 miles an hour or 30?
Right. They're assuming that you understand the basic ideas of speed limits between here and there. That's what I mean. But even if it's just, you can imagine an ancient person doing
It's
this.
an hour away. If I'm traveling by worm.
Right. What if I'm traveling by tube?
Dude, it's really interesting that you bring that up because you guys know Texas is a state with interstate highways everywhere, right? Like you go 70. Something's an hour away, it's like 60, 70 miles.
Yeah.
Dude, in Maine, I go places 20 miles away, it's an hour and 15-minute drive.
Yeah.
Not
So, like, it's crazy. You say that, like, now when someone, I'm like, hey, how far away is it? And they're like, oh, it's about 15, 20 miles. That completely throws me. I'm screwed.
Well, they obviously have a small sky. 'Cause, you know, the bigger the sky, the faster you go.
That's right. But even if it's, you can imagine, like in ancient times, if it's, you know, if you said, well, how far away is that guy's farm from yours? And he'd say, oh, it takes me about an hour to get there. If he's talking about walking, right?
Yeah.
So if that farmer who is talking about going from one farm to another doesn't have any standard of measurement, you know, and I guess he wouldn't have a standard.
By noon.
Yeah, I can get there by the time
noon.
Yeah, by the time the sun is. If I leave when I wake up at dawn, I can get there before the sun is, you know, at its highest point in the sky. He's still not giving you a distance. That's a time measurement. So those things are connected and probably have been for a long time in people's
That's
minds.
what I was saying. You would come to that relationship naturally, starting from no standard.
Yeah.
Because speed or velocity is distance over time. You can't escape it.
But we think of it like, or I typically think of it in terms of like, well, what's a unit of measure for, you know, like a measure of distance? Well, we already have these things that, you know, so you think of like a foot and here's how long it is, but without realizing that was ultimately derived using time and space.
Yeah.
Yeah.
Because that's how it begins, right? That's the first connection you're making, as you're pointing out.
Yeah.
That it takes this much time to get there by the known standard means of travel.
Yeah, that's right.
And then, well, how do we divide that into smaller bits?
Yeah.
That's just cool. I think.
And then what about like on the other end of it? Right now, our standard for measuring time is the vibration of the cesium atom, which is a movement in space.
Yep.
You know, so they measure, you know, it vibrates so many trillions of times, I don't know, per second. And then that gives you, I don't, it's probably not that many times, but that gives you the length of the second. And so what they're measuring is something moving back and forth in space and counting that. And that gives you.
But is it in whole numbers, or are they still like, in order to make it a fraction of the rotation of the Earth?
Oh, I don't know.
Are they just calculating like, well, it's not in whole numbers? In other words, like, well, when it does it like 1.2 times, right? You see what I'm saying?
Oh, okay. So it has to be a specific temperature, right?
Oh gosh.
Yeah.
Yes,
so now you've got energy states.
Okay. So the funny thing about that though is, Russ, do you know why they developed the atomic clock?
It had something to do with satellites, right?
The Earth's rotation is slowing down.
Ah, okay. And it's slowing down
so
appreciably.
As it rotates slower, the second's length changes if you're basing the second on the rotation of the Earth through its daily cycle.
Right.
So
they needed
it.
They needed a standard that didn't change as much as what the old standard was changing. Yeah.
Oh wow.
So they came to the cesium atom and that standardized it because it isn't slowing down.
Right. So this is about precision, right?
Right.
Up until a certain time,
we didn't need
very recently, we didn't need it to be that precise, but we're building more and more precise computers and electronics.
When I start recording multiple tracks, I need precision timing.
You need precision timing. Yeah. So the cesium atom vibration, which has to be done at a specific temperature, so the whole thing is done in this enclosed, protected or whatever, and they count it. And it is based on, the initial count was based on the old standard of a second, and now they just keep it at that standard.
Yeah.
Right?
So it's probably not a whole number. It's like it does it 3 times, that's a second. It's probably...
Yeah.
Or maybe it's going so ridiculously
it's
fast.
really
You
fast.
can't give it a whole number.
It's doing it millions and maybe billions of times. Yeah.
Watcher.
How many times does a cesium atom vibrate? And what is the count there, Watcher? Can you figure that out? I know it's a high. I'm pretty sure it's a high number.
Yeah.
Yeah. But that gives you a high degree of precision.
If the frequency, I'm thinking it could be a lot. A lot.
It has a frequency of exactly 9,192,631,770 hertz.
There you go.
Type it
So 9.192,631,77 gigahertz. That's its.
Yeah.
That's its.
So that's a high degree of precision, right?
Yeah.
If somehow that atom vibrates a little bit differently, you maybe get like, 1/10 billionth of a second off for that count.
Yeah.
So that's a high degree of precision.
And if that was slowing down slowly over time, we wouldn't really know.
Right. You would have to be able to measure it against something else.
Yeah.
And be like, wait a minute.
These are changing in relationship to each other. And
Didn't they initially want to do this with light? Wasn't there something about the frequency of, somebody wanted to use lasers way before they did the cesium clock. So they were thinking ahead. I'm trying to remember if this is correct. And then 20 years later, maybe 30 years later, the cesium atomic clock was adopted to get higher precision. But somebody had thought of it in terms of the frequency of light at a particular kind of laser and counting that. Yeah.
I wonder if that was also a cesium laser.
Could be. I don't know. But it's just really fascinating when you look at the history of metrology. That this is what you find out, that distance and time have been intimately related in discovering standards and then making them and then interconnecting them in these like spider webs, right? So that they like there's multiple. And what's interesting about that is that, number one, there's multiple ways you can check your standard because it has multiple standards, large and small astronomical cycles, divisions of this or fractions of that based on other kinds of measurements.
Yeah.
And the fact that all of those things can be connected that way is also interesting.
So I wonder why wouldn't we in modern times, we've developed a new system of measurement based on, other more precise physics that we've discovered, a new way to standardize time or the counting of time, seconds and all that. But because our time calculations are related to the motions of our local system, and yet we're still using this calendar that we have to let's add a day and then we'll subtract a day and then we'll wait for 4 years and we'll add a day.
Yeah. Why is it? Why is that?
When will we adopt a new system that incorporates so that everything is the proper length of time so that it just works out? Right?
Yeah.
Obviously, you would have to make minute adjustments, but they could be less than
A day every 4 years.
Yeah, because what we're doing by doing the leap year thing is we're getting too far ahead of the clock, and then we're going too far behind it, and then back too far ahead of it, and then too far behind it, and eventually we have to do another correction of a full day, or an hour, or whatever. I can't remember how it works. That's we can do this jumping too far ahead and too far behind for so long, and then we have to do something special let's not jump ahead this time. And that'll put us a little bit too far behind so that we can jump ahead too far again, but not be too
not
far.
as far as we were before. Not be too far, too far.
So optical clocks, Russ, are actually the next step. They've developed ones with strontium lasers that are accurate down to 10 to the negative 21.
Holy crap.
Right. So, and they keep getting more accurate. They think by 2030 they'll have an atomic clock that's accurate down to
an optical clock.
Yeah. So they use lasers and periodicity of the laser, which, sure, I need a second that is so accurate that it has an uncertainty of 10 to the negative 60.
But you do if you're using electronics that require that kind of accuracy.
Yeah, all right. So
the thing you're using to talk to us with needs that accuracy, Watcher.
Yeah, so I don't have to spend so much time editing Cosmo shows.
You know what's actually crazy to me? Am I the only one who's wondered, if somebody with the HSMF standard goes to that Mohenjo-Daro pool and looks at the bricks and goes, "You guys built this a third slower than you had to. You could have just sped it up if you would have used bricks this size. You guys are dumb."
Well, yeah. It's a
Our
fascinating
society
topic
is
to me.
3 times as advanced as yours.
So does that imply other things about these stone circles? They couldn't possibly have been... Well, I shouldn't say that. It seems...
It's highly improbable that...
No, I don't even know if I should say it that way. It just seems... Because people like to think of them as ways to measure the movements of the heavens. And yet I'm saying the way they built them implies they already had incredibly accurate measurements. They didn't need to do that. It's something else. Yeah.
That's a
really good point.
I
hadn't thought of it in those terms that no. You guys are putting the emphasis on the wrong syllable. They align that way because they knew that
already
when they built them.
Yes.
They don't need to measure it because they can't measure it if they don't know it already.
They may have wanted to continue monitoring it. It just doesn't seem like these things were for discovering those things.
Right.
But we build incredibly accurate, precise, ground-based telescopes now that have lots of these kinds of things built into them as well. But we're still using them to monitor the stars and study these motions, and not necessarily these astronomers that are using these telescopes aren't doing things like measuring precession, but
they should be.
They could, yeah. I'm just saying that. that they're not counting the precise number of days in a solar year.
Right.
Yeah, so at the end of the article, they're talking about basically like petroglyphs, little carvings on the wall that are still to this measurement system.
Yeah.
Or at least extremely close.
Right.
So it'd be like, somebody having a ruler that's made
Using that as a standard,
be
basically.
the foot,
Yeah.
and be like, well, I'm going to make this about a foot wide or whatever, and use the ruler, and you're doing it.
And he jounced it a little bit.
Yeah, you don't get it
Quite
I mean,
right.
you get it accurate, but it's not, it just depends on how.
Yeah, it's hand accurate using an accurate measuring tool,
Yes.
right? Just like you would with a ruler, which is very precise,
so-
but you don't necessarily make a precise measurement.
So the carving is not something that you're using to measure the cosmos or
Yeah.
the motions of the earth or time or anything
Right,
like that.
yeah.
But it is based on those things.
Yeah.
So that's, to your point, like they're building the structure already knowing these things, but still using it for observation, like
Yeah.
further observation.
Yeah, yeah.
Let's build it as accurately as we can based on what we know
Yeah.
and continue to make observations.
Yeah. And check our work, right?
Yeah. But it also suggests that like if, and let's do this scenario again. Like if we had some cataclysm and then we're scattered civilization living on the bones of our advanced society, where we have these ideas, we have this knowledge, and there's some people surviving that obviously know how to build and all this kind of stuff, and we're applying to the best of our ability the knowledge from the civilization that fell. We would be building sites or observation sites to try to maintain
Yeah.
or continue that knowledge, and we're building them to those, at least to the best of our ability, to those standards.
Yeah.
So that's, I don't know. It's like you could look at it either way. It's like,
Or maybe if you like anticipate a cataclysm, you have the measurements built into this megalithic structure that you can come back like with a length of rope and lay it out on the diagonal at Stonehenge and go, all right, I got 10 holy shoot mother flipping feet on this rope.
I don't
Because
know.
I know
seems,
that that's what's here. So you can then take that and, just, I don't know.
yeah, for a stone circle, I'm not sure. I mean, like that seems like something that you would build after the fact.
Yeah.
I don't know why, but to me,
I would take one stone block and cut one, holy shoot mother flipping cube into it, and then you would have the measurement, and if that survives the cataclysm, then you can say, okay, the dimensions of this cube that have been cut out of this stone block are exactly one.
That's what I'm
mother
saying.
flipping foot.
If you did it before the destruction, then you could use all the modern tools and all the standards and the measurement tools to make everything very precisely.
Yeah.
After the fact, you would know, like, well, here's how we got.
Yeah.
You would know that the measurements are inside everything. Like they're contained within them in some way, shape, or
Well,
form.
you would just know that the measurement was possible. The standard was possible.
The standard was possible, and how to.
And maybe you're trying to reacquire it. Because
Like-
what it really is about is like you have to be able to measure the thing you measure against. That's the key, right?
That is it, yeah.
So like we
Well,
wouldn't
like-
be able to rebuild the cesium atomic clock.
Right.
So we would say, okay, now we need our standard of time back. We can no longer use this atomic clock anymore. So we go back to counting seconds by very carefully measuring the movements of heavenly bodies.
Yeah, and then you might still have some measuring tapes.
Yeah.
So you use those to lay it out.
Right. And those are also based on
Yeah.
older versions of the same kind of system. Yeah.
So I'm looking at the floor in my hotel room, and I realize that if I
mean
ever
your
was
space
in a
station?
world, that one, without a ruler, I have 1 foot by 1 foot tiles.
Yeah.
But it's only because I know that that's built into the system.
Right.
So,
But if there's a cataclysm, your grandkids may not.
they're going to have no idea.
Right, but they may find lots of things that are basically that length.
Right.
And
they
say,
can
this
then-
must have been a standard, and we could, if I just take the edge of this tile and make my own stick, you know, that I can carry around with me, that's the same length, then they'd basically be using the modern foot. And maybe they
That
could come back
actually-
around to how that was derived in the future.
You know, it really kind of goes back to your point of how building these, you know, cosmologically aligned structures obviously shows they already had that.
Yeah.
Because if you just take that stick off of that tile, you're not going to then go set up Stonehenge.
Right.
Because no. But if you knew that ahead of time, you could, yeah. I've never thought of it that way. That's actually, I feel kind of dumb for never thinking of it that way because it's pretty obvious to me now. That's crazy.
Yeah, I find it interesting. It's like archaeoastronomy is about learning how these archaeological sites are astronomically aligned, but there's also this implication that that's because they were deriving these same measurements that the sites are used to, they're built around, and it just doesn't. Unless they were,
Because we're learning about those measurements, we assume they were learning too, instead of just accepting that they already knew them. That's crazy.
Yeah, I think the point that you made earlier that like you don't build Stonehenge from like without already knowing the system of measurement. So that's the question. Like, is this built because they were? It's like the more accurate your measurement becomes, you build a new site when you reach like this point where you're like, okay, we have a much more accurate system now. Let's build a new site.
okay. Yeah,
Because they could start like with a simple standing stones, simple observations, and then, you know, scholars like you're saying are like observing the motions in the heavens. Other people are working on distances and all this kind of stuff, and they're coming together and they're saying, okay, we have a breakthrough. Like we've got this new unit of measurement. Let's build a new site. Use that unit of measurement to observe the heavens, and then they might find like, well, it's off. It's not quite accurate. Like this and that. Build another one. So you could say that this is that the stone circles could have an evolution.
Yeah.
In their ability to become more and more precise. What makes it really interesting is that these things appear all over the planet.
Yeah. Yep.
And so that kind of begs the question, like, well, wait a minute. Was this knowledge widespread? And again, it's like the pyramids question. Why was everybody building giant triangles? Like, was it just, this is just what people do when they're figuring this stuff out, and we'll do it again after the next cataclysm? We'll all start building circles and then triangles. Or is it because they inherited something in the first place?
Yeah.
And they're using that inherited knowledge to lay out the construction of something that's going to give them better you know, observational and the ability to teach, you know, with working with it, or, you know, because it's one thing to explain it to somebody. It's another thing to build it like from the ground up and then make the observations yourself and understand it.
It could be schools.
On a fundamental level.
For sure.
Yeah.
And the other thing is
and it's like our schools today are also areas of study. It's not just a school is not just a place to teach. It's a place for the teachers to also learn.
Yeah. Yes, but the institutes of higher learning are supposed to be places where you also do research,
the entire
stretching knowledge.
Yeah.
Yeah.
We are also learning as a species about the universe at the places where we're teaching about the universe.
And the other thing that's not included in all this, we've been talking about measurements of space and time, is weight. Like, you know, if you think of commerce, like a big one is like you need standards of weight.
Standards of weight.
You know, like how many beans are you selling? Like, you're not going to count the freaking beans. You just want to know how much they weigh.
Right.
So that you, as a guy who grows beans and sells them in the market, you're giving people, you're like, I've got a bag of beans, I've got 100 bag of beans behind me. They all weigh the same.
Yeah.
Because I'm trying to do this you know, like I'm trying to divide my produce.
So then you come at, oh man, yeah. So you
So how do you come up with like,
You
well, what's
come
a
up-
standard of weight, and then I gotta have the scale.
yeah, you get
know?
this chunk of gold, right? And you realize like, okay, gold seems to be pretty, like you have 2 pieces of gold. Let's make them the same size.
Yeah.
What size shall we make them?
How do we do this?
Well, let's combine it with
So-
time in some way and make them the same size, and then they'll be the same weight.
I don't know if you guys are aware of the big breakthrough with that.
Please tell us.
Was okay, so displacement of water.
Yeah. Yes. Yes. Exactly.
Yeah.
The water.
Eureka!
Water can absorb gas.
That's right, and it has to be the right temperature.
Yeah, but like you would standardize your weights based on
Water
their
can have salt
displacement
in
of
it.
water from like a measured tub of water.
Yeah.
Is it distilled? It has to
It has to be distilled water.
Yeah,
And
because a milliliter of water is equal to a gram. If it displaces 50 milliliters, it's a 50 gram weight.
How do you know how many milliliters you have?
No, you can't.
That's
no,
what I was
you can't-
saying
you
about
can't-
the
no,
gold.
You can't go there.
It's the same
No.
thing about a chunk of gold, right? You're imagining that the gold is the same, just like the water would be the same. Well, now let's like standardize the amount. Well, how do you do that? Well, you have to measure it in 3 dimensions.
Yeah.
You also have to perform metallurgy on the gold to
Yeah. How pure is the
purify
gold?
it.
Yeah. My point is that you have to measure it in 3 dimensions.
Yes.
You know, if it's water that you're measuring,
And if you're measuring it in 3 dimensions, you need a standard of
need a
measure.
standard of measure.
Distance.
distance, which is connected to time, which is connected
right.
to weight. Which
It's
is connected
amazing.
to distances. Damn it.
Well,
I
think
can
that we
say for one thing, I don't know how all this happened, but this show is too long.
It is too long.
it's because the thing that makes Ahura Mazda most happy is long shows,
That's right.
and also pyramids, triangles, circles.
Yes,
Those all make Ahura Mazda most happy.
it does. All right, guys. Hope you enjoyed this. Get a hold of us, brothers of the serpent at gmail.com. Check out the website. It does make Ahura Mazda most happy. If you check out the website, brothersoftheserpent.com. Join the pyramid scheme. You can support us through Patreon or PayPal. On Patreon, we do have special stuff being posted. Patreon shows we do on occasion. We're posting bumper music there and other stuff, other goodies, old commercials, spoof commercials that we made, and other things. Join the Facebook group if you want. Join the Discord. That's the big chat we have. Discord server. You can get to that through the website as well. Thanks to History Shift, who's made our YouTube channel possible. And thanks to all of you listeners out there. We love you guys.
Always have.
Always will.
Good night, Adamu.
Get back to work. Kyle's still pointing at me.